7 learning objectives relate to the forces section of A.2 Forces and Momentum. We're going to start by looking at Newton's 3 laws of motion, which is learning objective 1, and describing forces as interactions between bodies, which is learning objective number 4. You will know from previous study that Newton's laws relate to forces, and we can't learn about Newton's laws unless you understand what a force is. And the best way to understand what a force is to learn a definition. The definition is a push or a pull that acts upon an object as a result of its interaction with another object. So let's look at the 3 examples here. We have a tiny man pushing on a massive finger. No idea why, but that's stock images for you. This is a push. There's an interaction between one object and another object. It's a contact interaction. They're in contact with each other. So we can describe that as a force. Let's look at the magnet below. There's a pull going on here. So it's a push or a pull. And there is 2 objects interacting with each other. Yep, that's good. In this case, it's non-contact, and we'll discuss what that means later. And finally, we have these satellites orbiting the Earth. There's a pull in action there to keep those satellites in orbit. There's 2 objects in interaction with each other, the satellites and the Earth, and it's non-contact. They're not touching each other. So we can describe all of these things as forces. And now we know what a force is, we can look at Newton's 3 laws. The first law, unsurprisingly, is called Newton's first law. The definition of Newton's first law is here, and this is something you'll have to memorise. An object will remain at rest or continue to move with a constant velocity unless acted upon by a resultant force. I'd like to really delve into this in a little bit more detail because there's 2 key elements here. And the first element is remain at rest. If we consider this football here, there will be 2 forces act upon this. It will have the force of weight, and it will have the normal or the reaction force. If you've never heard of these forces before, don't worry, we will go over them later. The key to these forces is they are balanced. The weight force equals the reaction force. And that's why the object remains at rest. When another force comes in, for example, this football boot, that external force means that the object will not remain at rest any longer, so Newton's first law does not apply any further. You may be saying, Sally, that's very simple, I'm bored of this. Well, I'm going to keep talking because there's another element to Newton's first law that's important. Let's look at this definition again. An object will remain at rest or continue to move with a constant velocity unless acted upon by a resultant external force. A lot of people think that Newton's first law only applies if the object is stationary or at rest, but that's not true. This rocket here is moving at a constant velocity. It's moving in a straight line and not changing speed. That means the forces on this object are balanced, and it also undergoes Newton's first law, unless it's acted upon by a resultant external force. And in this case, we're looking at the engines being turned on. This will become really important when you tackle exam questions later on. So when you're remembering Newton's first law, don't forget this element of or continue to move with a constant velocity. It's really important, not only just to get full marks when they ask you to define Newton's first law, but also to actually answer the questions. Let's move on to Newton's second law. Earlier we had an object in Newton's first law and the forces were balanced on either side. So let's just say that's thrust and that's friction. In Newton's first law, the value of thrust would be equal to the value of friction. In Newton's second law, that is not true. You can see here, this is Newton's first law. The value of thrust is 100 newtons and the value of friction is 100 newtons. So there's no acceleration. That object is undergoing Newton's first law. As soon as those forces become unbalanced, then Newton's second law applies because it causes acceleration. So if we look at the second situation here, we have thrust is equal to 200 newtons, friction is equal to 100 newtons. That means there is a resultant force of 100 newtons towards the right, and that resultant force causes an acceleration. Similarly, in this third situation, we have 300 newtons going to the right, 100 newtons of friction. The resultant force is 200 newtons, and that resultant force causes an acceleration. The sum of all forces acting on the object are not equal to zero. I guess a good way of saying Newton's second law would be the acceleration of a body with constant mass is proportional to the resultant force applied in the direction of the force. That is such a lot of words, but useful for you to put down in your definition section. You'll know that a graph, a proportional graph, directly proportional graph, has the two quantities that are in direct proportion on either axis. It's a straight line through zero. If you are considering Newton's second law, you would say that force is proportional to acceleration. But if we want to make that into a formula, we have to say equals, and there's a constant of proportionality. This is a constant of proportionality. And what you find if you do any form of experiment with Newton's second law is that constant of proportionality is equal to the mass of the object that is being accelerated. F equals ma. And F equals ma is basically the short way of writing Newton's second law. I wouldn't get too cocky about using Newton's second law. There are two situations in particular that are quite tricky to work through. Those situations are when you're dealing with pulleys, and the other situation is when you're dealing with elevators, or lifts as we call them in the UK. So for that reason, I've put two separate tutorials below this, just giving you some ideas on how to solve Newton's second law problems when we're looking at pulleys or elevators. On to Newton's third law. If a body A exerts a force on body B will exert an equal and opposite force on body A. Let's call Earth body A and the Moon body B. The Earth exerts a force on the Moon, and the Moon exerts an equal and opposite force on the Earth. That's it. And you'll find that there's certain laws that need to be followed to see if we are looking at a Newton's third law pair, and we'll discuss that a little bit later on in this tutorial. For the moment, can you head to your revision note template, and in the definition section, can you write down Newton's laws 1, 2, 3 in your revision note template, and also write down the definition of a force. Pop that in there as well. Download A2 Part 1 knowledge questions and attempt questions 1 to 8. That will help you apply all this stuff we've been talking about and makes you understand it. Next, we're moving on to learning objective 2, which is solve translational equilibrium problems using Newton's first law. And learning objective 5, draw free body diagrams and analyse them to find the resultant force on a system in 1 and 2 dimensions only. Gosh, well that sounds complicated, doesn't it? It's not really, don't worry. Let's move on. Translational equilibrium is when the resulting force acting on the body must be zero. That's a definition of translational equilibrium. Now we've found before when we were looking at Newton's first law, if the resultant force is zero, then the object is at rest or it's travelling at a constant speed. And that's the clue we need when we are looking at exam papers. Exam papers, and examiners in particular, always give you a clue when you have to do problems on translational equilibrium. And you can see some of these exam questions here. Constant speed, constant velocity, constant speed, constant velocity, constant speed, steady speed, constant velocity. Let's keep going. Stationary, at rest, equilibrium. The force in one direction equals the force in the other direction. So in this case, thrust and friction. Thrust is equal to friction. If that's 100 newtons and that's 100 newtons, then 100 equals 100. We get it, right? If something's falling, then the weight is equal to the drag force So if the weight is 50 newtons, the drag force is 50 newtons, that would be falling at a constant speed. Therefore, it's in translational equilibrium. And that's when you're looking at two forces. One goes in one direction, the other goes in the other direction, and they're balanced. There is the situation where you might have three forces. And for three forces, the following rules apply. All horizontal components of force add to 0, and all vertical components of force add to 0. We have three forces here. We've got the tension force of 65 newtons. We've got a force pulling this ball that way. That would just be somebody holding it. And we have the force of weight pulling it down. There are three forces acting on this object. Let's look at the horizontal components of force. The horizontal in that direction is 43.5 newtons. And if you were to work out the component of this tension force in the left-hand direction, you would find that the horizontal component is 43.5 newtons, because all horizontal components of force add to 0. Similarly, if we look at the vertical components, the vertical component downwards is 48.3 newtons, and if you take the vertical component of the 65 newtons and work it out, the vertical component would also be 48.3 newtons. So all vertical components of force add to 0 as well. All forces cancel. If you find yourself in a problem where there are three forces in translational equilibrium, what you have to do is break it down into what are the components of forces acting left, what are the components of forces acting right, what are the components of forces acting upwards, and what are the component forces acting downwards. All the horizontal ones are equal and all the vertical ones are equal. This brings us on to a bit of feedback from the examiners. The examiners have told us that very few candidates have the ability to treat a body as a single particle and analyse the forces acting. What does that mean? Well, it means that very few students are able to draw a free body diagram. And a free body diagram is when you look at an object, for example, this box sliding down a hill, and you turn it into a single point mass with all the force arrows acting from that point and ensuring that all those force arrows are to scale and at the correct angle. The centre of gravity of this box would be here, and then what we'd want to do is just add arrows to that centre of gravity or that point mass to make sure that we're representing the forces correctly in the right direction and the right length. Here are the rules for free body diagrams and forces questions when we're looking at translational equilibrium. Look for the phrases constant speed or velocity, equilibrium, stationary, at rest. At that point, you know all the forces are balanced, or the resultant force is equal to 0. Draw a free body diagram, and this is one of the biggest mistakes that most students make. If you don't draw a free body diagram, you're likely to miss things out. It's really important. And finally, make sure all forces are equal in all directions. I think it would be a good idea now to take you through an example using these rules to show you how you would apply it in an exam situation. Here we go. Rule number 1 was to look for certain phrases in a question to give you a hint that you're looking to apply Newton's first law. And those phrases were constant speed, constant velocity, steady velocity, at rest, equilibrium, and so on. So let's go through this question. An athlete trains by dragging a heavy load across a rough horizontal surface. Here's our athlete here. There's a heavy load there and he's dragging it along, and it's a rough horizontal surface. The athlete exerts a force of magnitude F on the load, that's our load there, at an angle of 25 degrees to the horizontal. Once the load is moving at a bing bong steady speed, the average horizontal frictional force acting on the load is 470 newtons. Calculate the average value of F that will enable the load to move at a bing bong constant speed. Rule number 1 has been applied, we know that we're dealing with Newton's first law. Rule number 2 was to draw a free body diagram. So the load that we're interested in, the mass that will become a point mass, is this load here. We'll draw that as a point. We know that 470 newtons act backwards along the frictional surface as friction. We know that the athlete exerts a force F in that direction. We don't know the magnitude of it, but we do know that it's at 25 degrees to the horizontal. We also know that this load has a certain weight. We don't know the value of the weight, but we do know a weight exists. And finally, we'll know that there's a reaction force applying in the opposite direction to weight. The reaction force won't be equal and opposite to the weight because this athlete is reducing that reaction force slightly by pulling it at an angle. What we do know is that this object is moving at a constant speed. So the frictional force going backwards is 470 newtons. That means that the force going to the right must also be 470 newtons. If this force were any other value, there would be an unbalanced force acting upon the load, and the load would undergo acceleration. We know it doesn't undergo acceleration. So this must be 470 newtons to balance that 470 newtons. That allows us to create a right angle triangle with 470 newtons on the adjacent side. The angle is 25 degrees and the hypotenuse is F. We can then use trigonometry, or SOHCAHTOA as some people know it, to work out what the value of H is, or the hypotenuse, which we also call F. So let's substitute our values in. Cos 25 equals 470 over F. Therefore, F equals 470 divided by cos 25. That gives us a value of 518.59 newtons. If we go back to the question, you can see that the data is given to two significant figures. So our answer should also be given to two significant figures. So our final answer for F is 520 newtons. Okay, back to our notes. I'd like you to write down the definition of translational equilibrium in your revision note template. If you go to the diagram section, I'd like you to draw an example of a free body diagram in the common diagram section. And I'd like you to answer questions 9 to 13 in A2 Part 1 knowledge questions. Let's look at Newton's third law in a little bit more detail and identify force pairs using Newton's third law. We already know that Newton's third law is defined as if body A exerts a force on body B will exert an equal and opposite force on body A. And I mentioned before that there are Newton's third law pairs all over the world and in the universe, because we have an example here of the Earth and the Moon. But let's look at the rules for Newton's third law force pairs. A pair of forces obeying Newton's third law will always have the forces acting on two separate bodies. That's rule number 1. Rule number 2 is both forces have exactly the same type of force. Rule number 3 is they will be equal in size. Rule number 4 is they are opposite in direction. And rule number 5 is they act in a straight line. If we can look at a force pair and say all of these 5 things apply, then we're looking at a Newton's third law pair. Here's an example of a man running. The first rule was, are the forces acting on two separate bodies? Well, one force is acting on the foot here, and the other force is acting on the earth. So yes, the first rule is adhered to. They are acting on two separate bodies. The second rule was, do they both have the same type of force? And the force acting on the foot is friction. The force acting on the earth is friction. So yes. The third rule was, are both forces equal in size? Yes, they are. The fourth rule was, are they opposite in direction? Yes, they are. And the fifth rule was, do they act in a straight line? Yes, they are. So this person running on the earth is an example of a Newton's third law pair. Let's look at another example. We have a book resting on a table, and the question says, do the following pair of forces adhere to Newton's third law? And the two forces are reaction force and weight of book. I'll tell you right now, this violates rule number 2 for Newton's third law, because we have a reaction force and a weight force. Those forces are not the same. So Newton's third law pair does not exist here. So let's look at my notes on this. Rule number 1 was they act on two separate bodies, and there's a book and a table. Fine. Rule number 2 was the forces must be the same. The force on the book is weight, but the force on the table is the reaction force. So these two forces are not the same type of force. However, they're both equal in size, they're both opposite, and they act in a straight line. So we were nearly there, but these forces do not adhere to Newton's third law. Please can you head to your revision note template and write down the 5 points or the rules that identify force pairs using Newton's third law. Then answer question 14 in A2 Part 1 knowledge questions. There are lots of different forces in IB physics, and they largely fall into two different groups: contact forces and non-contact forces or field forces. The IB syllabus specifies all the forces that you need to understand, and we'll talk through them right now. So let's look at contact forces first. And contact forces are ones that you come into contact with. The first one we look at, and we've seen a little bit already, is the normal force. And sometimes it's called the reaction force. In IB physics, it's given the notation F subscore N. The definition of the normal force is the component of the contact force acting perpendicular to the surface that counters the body. We've already seen that when we considered the book resting on the table earlier. You can see that the normal force is acting perpendicular to the surface in contact, and the weight force is causing that contact force. If we have somebody resting against a wall, the normal force is perpendicular to the hard surface. If we consider a ball rolling down a hill, the normal force is perpendicular to the hard surface. That's the key point for reaction force, or the normal force, that it's always acting perpendicular to the surface in contact. Next, we'll look at the frictional force, and in IB physics, the notation is given F subscore F. The definition is the surface frictional force acting in a direction parallel to the surface of the plane contact between a body and surface. So you can see this frictional force here with the box being pushed along the surface. That frictional force is parallel to the surface of the plane contact, and it's in the opposite direction. So this box is moving that way, so the frictional force is moving this way. Look at the car. The car is moving this way, so the frictional force is moving that way, and it is in parallel to the contact surface. There are two different types of friction that you should be aware of: static friction and dynamic friction, and they're both being given these formulae here. I know you'll want an extra tutorial on this, so I've added an extra tutorial on static and dynamic friction for you below, just to delve into that in a little bit more detail. The next contact force we'll look at is elastic force, and in IB physics it's given the notation F underscore H. The definition of the elastic force is the elastic force exerted by a material when it is stretched or compressed and tries to return to its original shape. This is all about Hooke's law, is FH is equal to minus Kx. So when you're discussing elastic force, you're inevitably going to be looking at Hooke's law. You've probably seen Hooke's law in relation to a spring, where it's been compressed or stretched, and that's where this all comes into play. The next contact force is called viscous drag force, and it is given the notation F_d. The definition is the resistive force exerted by a fluid on an object moving through it. The example we have here is a ball bearing moving downwards through castor oil as a result of its weight, and as a force acting backwards resisting its motion, which is drag, a bit like friction, and it's eventually going to balance out and cause a constant speed here. The key point of this is the viscous drag force is greater in thicker fluids. So if you have a fluid that's got a high viscosity like honey, castor oil, then that drag force, that viscous drag force, is going to be greater. There is a formula for a small sphere falling through a fluid, and this formula for viscous drag force, 6 pi nu r v, where nu is the fluid viscosity, and that would be given to you. R is the radius of the sphere, and v is the velocity of the sphere. You'll be expected to use that equation in exam questions. And our final contact force is buoyancy force. Buoyancy force is given the notation Fb. The definition is the upward force acting on a body due to the displacement of fluid. If we look at the iceberg here, this iceberg is floating. And the reason it's floating is this volume of seawater here has been displaced by the iceberg. The actual iceberg has taken its place. And that displacement of that seawater causes a buoyancy force upwards. And it's governed by Archimedes' principle. The formula for buoyancy force is Fb equals rho, which is density, V, which is volume, and G, which is the gravitational field force. Let's now consider non-contact forces. When we looked at forces at the very beginning, we noticed that satellites were in orbit with the Earth, magnets were pulling things towards it, but nothing was actually touching. And those things are called non-contact forces or field forces. We're going to look at 3 in particular. Gravitational force has the notation F_g. Sometimes it's called weight, and if you look in the example of the apple here, it would have a weight. But if you look at the example of the Earth and the Moon, then you wouldn't call that weight, you'd call that the gravitational force. So it really depends on what situation you're looking at. The definition of gravitational force, and we go into this in much more detail later on in the IB Physics course, is a force that attracts 2 objects with mass towards each other. And the key point here is all objects with mass exert gravitational forces. The larger the mass, the stronger the gravitational pull. The next non-contact force is electric force. It has the notation F_E. The definition is the push or a pull between charged objects or particles. And again, we're going to look at this in much more detail later on in the IB course. The key point here is that opposites attract. You can see these 2 charges, positive and negative, they are opposites to each other, so they attract, they pull towards each other. The opposite happens when you have like charges, and this poor little baby's hair is standing on end because every single strand of this baby's hair has an excess of electrons. And an electron doesn't really like another electron, they repel. And that's what's causing this poor little baby's hair to stand on end and repel from each other. Finally, magnetic force, which has the notation F_m. The definition of the magnetic force is the force of attraction or repulsion between 2 objects due to their magnetic properties. And again, just like charges, like magnetic poles repel and unlike magnetic poles attract. Let's head to your revision notes. Write down the definition of any force you didn't know already. Go to the formula section, write down all the formulae associated with these contact forces, and finally go to questions 15 and 16 in A2 Part 1 knowledge questions and try them. We've got to the end of Part 1, of this massive topic. Once you've done the work here, let's move on to part 2. We can now begin part 2 of our very long topic, A2 Forces and Momentum. And part 2 looks at momentum. There are 5 learning objectives that we're interested in. These learning objectives range from 8 down to 12 in your learning objectives checklist. Without further ado, let's start with number 8. Define linear momentum and understand that it remains constant unless the system is acted upon by a resultant external force. And at the same time, we'll look at A2.11, solve problems using momentum and impulse for collisions and explosions, one-dimensional for SL and two-dimensional for HL. Okay, let's define linear momentum. Linear momentum is defined as the product of mass and velocity of an object. And in fact, it's almost always acceptable just to define it as the formula. Momentum is given the notation P equals mv. You'll notice there's arrows above P and V. That's just to denote that momentum and velocity are vectors. So linear momentum is a vector quantity. It does matter what direction we look at for momentum. The units of momentum, you can actually use 2 different units. You can use kilograms meters per second squared. And that's because the units of mass is kilograms and the units of velocity is meters per second squared. So you put them together and you get kilograms meters per second squared. But there's also the opportunity to use Newton seconds. Why can we use Newton seconds? Well, let's consider the formula for force, which we know of course has units of newtons. The formula is MA. So the units of newtons can also be written as kilograms meters per second squared. And these are all SI units, they're all fundamental units. We're nearly at the stage where we have the same units as momentum, but this s to the minus 2 is an issue. So if we take the units here and multiply it by s, then what we get is kg ms to the minus 1, and that is the equivalent of Newton's seconds. So Newton's seconds is the same as kilograms meters per second, and they can both be used as units for linear momentum. When an object is travelling along, here's my car. It's terrible, isn't it? It has mass, it has velocity. You can work out what the momentum is. Easy. We're kind of interested more in momentum when we look at things crashing or colliding or exploding. We're looking at the interaction of this car doing something. And that's where the conservation of momentum comes in. The law of conservation of momentum states that during any interaction where no external forces act, the total linear momentum is conserved in any specified direction. So what does that mean? It means the car that we looked at earlier crashes, then the momentum before that crash is the same as the momentum afterwards, as long as there's no external forces acting. And that looks mathematically like the total momentum before a collision is equal to the total momentum after a collision. And you can see they're both vector quantities, so direction does matter. The main thing that you'll be asked to do in an IB physics exam is solve a problem to find out what the velocity of an object is after a collision, or what the total mass of an object is, using this idea of the conservation of momentum. And there's a set of 5 rules that I would use to make sure you answer those questions perfectly. The first rule is the clue that you're using momentum and the conservation of momentum. The clue is you'll see the words collision, explosion, or you might even see the word momentum, which would be the biggest clue. Then you draw a diagram. On the left-hand side, you draw a diagram of the situation before the collision, and on the right-hand side, you draw a diagram of the situation after the collision. Rule number 3 is to choose a direction as positive. Number 4 is to apply momentum to each body before and after the collision. And number 5 is to remember that momentum before equals momentum after. Now, does that sound complicated? Well, let me show you an example of me using these 5 rules, and I think it will make things a lot simpler for you. Let's go. Rule number 1 of momentum questions is to look for a clue that the question is actually about momentum. obvious words might be momentum in the question. That would be a hint. But also words like impact, collision, explosion. This question here is about an air rifle pellet that's fired into a block of modelling clay. The pellet remains inside the clay. So what happens is that the pellet is being fired at a clay block. After it's been fired, the pellet remains inside the clay block and it moves together after the collision. Oh, here we go. Here's the word collision. Rule number 1 has been found. We now know that this question is about momentum. We're given a set of data here and we were asked to show that the initial speed of the clay block after the collision is 4.8 meters per second. So rule number 2 was to draw a diagram before and after the collision. So I tend to do it in the form of a table. I'll have the word before here. Oh, my writing's dreadful there, sorry. And after. Before, we have a pellet that has a mass of 2 grams and a velocity of 140 meters per second, and that's given in the question. That is being fired at a stationary mass of clay, which has a mass of 56 grams and a velocity of 0. After the collision, the bullet goes inside the clay, so we're now acting as one mass. So that's mass 1 plus mass 2 equals 58 grams, and we'd like to know how fast it's travelling. We need to choose a direction as positive, and I think in this example it makes a great amount of sense to choose the right as positive. So anything that moves in that direction in our example is going to be positive, and anything that moves in the other direction, in the left direction, will be negative. So now we apply the momentum formula for each of them. m1v1 plus m2v2 equals m1 plus m2, or mass times velocity. For the second one, the reason we can say there is an equal sign there is because of the conservation of total momentum before equals total momentum afterwards in the absence of external forces. So we pop in our numbers, 2 times 140, and it's all going in that direction, plus 56 times 0 equals 58 times v. So we have 280 equals 58v. V equals 4.828 meters per second. All the data is given to 2 significant figures, so V equals 4.8 meters per second. And if we go back to the original question, we have proved the answer. Now we've chatted through the definition of linear momentum and we understand what the conservation of momentum is. Can you note both of them down in your revision note template? And now I'd like you to go and try questions 1 to 5 in A2 Part 2 knowledge questions and use the rules that I've just talked you through. Use them to try and answer those questions properly. In the last section we talked about momentum and how we can analyse the momentum before a collision and the momentum after a collision. In this section I'm interested in what's happening during the collision. What's happening at that point where the momentum has been changed from one point to another. And that concept, it all revolves around something called impulse. Learning objectives 9, 10 and 11 all deal with the concept of impulse. As I said before, we're thinking about momentum changing. And we noticed earlier in the exam questions that we're looking for the words collision, explosion, maybe even the word momentum. But during this collision, or during the explosion, a force must act on an object during a very short period of time. And if we take this example here, before the collision we have a ball heading towards a wall. And after the collision, the ball moves away from the wall. It's got a different speed, but it's got the same mass because it's the same ball. At the point of collision here, there must have been a force acting on the ball over a short period of time that caused that change in momentum. And it's this point of the causing of the change in momentum that I'm interested in. But before we go into defining impulse and the point of change in momentum, I'd like to take us right back to Newton's second law, because we've already previously defined Newton's second law as F equals ma, and we've said, force is proportional to acceleration and the constant of proportionality is mass. That's a more popular known version of Newton's second law. But Newton didn't actually define his second law like that. Newton defined his second law in these words. He said, the rate of change of momentum of a body is equal to the resultant force acting on the body. Rate of change of momentum. If you were to represent that in maths, you'd say rate of change of momentum. Rate of change means divide by time. How quickly is something changing with respect to time? So the rate of change of momentum is equal to the resultant force acting on the body. So actually, Newton's second law in a mathematical form is F equals delta P over delta T. Let's try and break that down a bit, because delta P just means the final momentum subtract the initial momentum. So the final momentum is mv, the initial momentum is mu, and this delta T, keep that the way it is. The mass is the same, so we can take that out. And what we're left with is m brackets v minus u over t. And of course, from A1 kinematics, you would know that v minus u over t is equal to a. So F equals ma. What is very clear, though, is when a force acts upon a body over a period of time, a change of momentum occurs. That's what I'm talking about here. When a force acts on a body over a short period of time, a change in momentum occurs. The momentum that way is different to the momentum that way. And that is the foundation of impulse. Impulse is defined as the change in momentum of an object, and it's given the symbol J. And J has the formula, the change in momentum, we can start with m delta v, but it's also got the formula F delta t. How did we get that? Well, let's go back to what we saw earlier. We saw this, which brought us to m delta v over delta t. So we've got F equals m delta v over delta t. So Ft equals m delta v, and both of those things are equal to J. They are both the formula for impulse. The units of impulse are kilograms meters per second, which is the same as momentum, which makes sense because that's the quantities in momentum, or Newton's seconds, which makes sense because the units of F times T is ns. It's also a vector quantity. So the key to remembering about impulse is that there's two expressions we can use to find the impulse of a collision or a change in momentum. Why does this matter? Well, impulse, you see it everywhere in real life. Once you understand it, you see it everywhere. Let's think about a car crashing. So we've got this car, heads towards a wall. It's got mass m and velocity v. So it's got an initial momentum. Hits the wall, okay, sadly. And its final momentum is equal to 0. There's a change in momentum there. That change in momentum is constant because it starts off with a constant mass and a constant velocity, and it ends up with quantities that aren't changed either. The change in momentum, this value here, is constant. What that means is if you can increase the time taken for any collision, then you must be able to decrease the force that is applied during that collision. And all of these situations here represent that concept of impulse. A seatbelt. What a seatbelt does is it stretches. And by stretching, it increases the time taken for you to stop, which means the force applied to you decreases and it doesn't hurt as much. A crumple zone. A crumple zone increases the time taken because it crumples, so it takes a longer time for the car to stop, which means the force on the car lessens. If you jump and bend your knees, by bending your knees, you're increasing the time it takes to stop and you're decreasing the force on your knees, thus saving your joints. And a tennis racket, what you actually want to do is increase the force on that ball on your tennis racket. So you want to decrease the amount of time it takes to change the momentum of the ball, which means you want a very tight string. So you want tight strings on your tennis racket to increase the force that the ball is released with. So impulse begins to allow us to explain real life situations. If I can just direct your attention up here for the moment, I think it's pretty easy to use this formula. There's not much in it. It should be relatively simple for you. That is, it's simple if the force is constant. It's simple because it's just a formula, you pop in the numbers. Here's a question for you though. Let's go back to these situations here. Do you think there's a constant force on the seatbelt as it's slowing you down? Do you think there's a constant force on the crumple zone as the car's stopping? Do you think there's a constant force on your knees or on the ball as it changes momentum? No, that force changes over time, and the way it changes over time tends to look like this graph here. It starts off with a small force, gets to a maximum force, and then as it changes direction and leaves, the force decreases again. So it's not always useful to use this equation. When the force is not constant, then we have to look to a graph to help us work out any quantities to do with impulse. And the key for you to remember here is that the area under a force time graph is equal to impulse. So if you are presented with a force time graph, you know you're dealing with impulse. You know you're dealing with change in momentum. Please can you get your revision note template out and in the definitions section write down the definition of impulse. I would like you to go to the common formulae section or the other notes section and write down the link between Newton's second law and momentum. Also write down the formula for impulse. Go to the common graph section and draw an annotated force time graph. And then finally do questions 6 to 9 in A2 part 2 of the knowledge questions. We come to the final part of the momentum section and we want to understand what an elastic collision is and an inelastic collision is, and explosion of course. And this section really delves back into what examiners have said in the past. Examiners have said that very few candidates seemed to know what was meant by an elastic collision. Now that is not going to be you. Let's look at inelastic and elastic collisions. We know from previously that momentum is conserved in all collisions, assuming no external forces apply. We can make lots of calculations with that simple knowledge. However, if you consider a collision, kinetic energy is not conserved because when a collision happens, it's going to lose energy. It's going to lose sound energy and heat energy. And if that happens, then this collision is inelastic. If it loses kinetic energy during a collision, then it's inelastic. I've got news for you. Most collisions and most explosions are inelastic. An elastic collision is one where kinetic energy is conserved. So if you take the kinetic energy of the ball here, before the collision down here, and you take the kinetic energy of the ball here after the collision, these two kinetic energies would be exactly the same. Can you imagine this happening in real life? Not particularly, no. Energy is lost in most collisions and explosions. So examples where it might happen would be in atomic collisions. Nevertheless, this is assessed in your IB physics exam, and you do need to know the difference between elastic and inelastic collisions, and you do have to make the calculations. So with that in mind, go to your revision note template, write down a definition of an elastic and an inelastic collision, and then answers questions 10 and 11 in A2 part 2 of your knowledge questions. We've finished the momentum section of A2 Forces and Momentum. Next section is looking at circular motion. We're doing it, let's go. The final part of A2 Forces and Momentum looks at circular motion, and it's the final 4 learning objectives of our learning objectives checklist. Let's start off with, quite a lot of them, number 13, 14 and 15. Velocity changes. I would like to consider a satellite orbiting the Earth. At V1, that speed is perhaps, let's say, 500 meters per second. And at V2, the speed is the same, it's 500 meters per second. It's a constant speed, but the velocity is changing. The velocity is changing because at V1, the direction is that way, and for V2, the direction is that way. If a velocity is changing, then the object is accelerating. And that's because acceleration is defined as the rate of change of velocity. And velocity clearly changes. With that knowledge, we can actually do a little bit of vector subtraction to find out what the direction of acceleration is for an object that's undergoing circular motion. We know that acceleration is defined as the rate of change of velocity. So we would like to find the change in velocity of this satellite that's shown around the Earth. And the change in velocity means the final velocity minus the initial velocity. And remember in A1, I taught you the trick on how to subtract vectors. It's the final velocity plus minus the initial velocity. So let's take that down to here. We want to subtract V1 here from V2 here. And to do that, we add V2 plus minus V1. Minus V1, now V1 isn't going that direction, so minus V1 is going in that direction. We're going to add vectors V2 and minus V1 tip to tail, and that will give you the resultant vector in this direction here. So the vector direction of the change in velocity, or the acceleration, is in this direction here. No matter what stage you do that around the circular motion, you always have the change in velocity vector directed towards the centre. The acceleration vector is always directed towards the centre, no matter where you do this simple vector subtraction. And feedback from the examiners in past have said candidates were unable to use a vector diagram to explain the need for a centripetal force in circular motion. Well, where's force coming into it? We've only really been talking about velocity and acceleration. Do you remember that if there's an acceleration, there must be a force applied to it? So if there's an acceleration towards the centre of the circle, there must be a force directed towards the centre of the circle. And that force is called centripetal force. Head to your revision note template and in the explain section or the other notes section, explain how an object travelling at a steady speed can be accelerating in your notes. And I would draw the change in velocity vector in your common diagrams section. On to the last but very large learning objective to do with circular motion. And it's understand and solve problems involving centripetal force, centripetal acceleration, period frequency, angular displacement, linear speed and angular velocity. For you, quite a lot to get through. Let's start very simply. We really want to understand radians and why they're used in physics. Okay, radians are often used because they're multiples of pi, which is a natural number and it's a natural unit for trigonometric functions. Physicists prefer radians. It links everything in much better. And the angle in radians is defined as the arc length divided by the radius. So you can see the arc length is here, divided by the radius, which is here. And if we compare it with degrees, degrees is based on dividing a circle into 360 equal parts, whereas radians is only based on the radius of the circle. It is important you understand that both degrees and radians can be used and understand that 90 degrees is equal to pi over 2 radians. 180 degrees is equal to pi radians. 360 degrees is equal to 2 pi radians, and so on. You should be able to convert between the two. I think it's now time to define angular displacement. Angular displacement is defined as the angle in radians or degrees through which a point has been rotated about a specific axis. You can see on the diagram here, the angular displacement is the angle through which a point has been rotated, and it's to do with the arc length and the radius. Let's have a look at linear velocity. Let's have a think about how fast something is moving around a circle. Linear velocity, or tangential velocity, is the velocity of a point on a rotating object. So if we think about a satellite orbiting Earth like we had earlier, then the tangential velocity is this. Okay, that's a terrible diagram, but there we go. And the formula for linear velocity is 2 pi r over t. You will recognise 2 pi r as the circumference, and the circumference is equal to a distance. So the linear velocity is equal to distance over time, which is 2 pi r over t. R is of course the radius of the point, and the units of linear velocity are meters per second, also written like this. If you consider a wheel, and we have 2 points, a red and a blue point, those points are placed on the wheel. The red point has a smaller radius than the blue point. And if we consider the equation v equals 2 pi r over t, then the red point has a smaller radius, which means it has a smaller linear velocity than the blue point. So when you're considering linear velocity, the radius may be smaller for something, which means that the linear velocity is smaller. However, let's now look at angular velocity. Angular velocity is given the symbol omega. Angular velocity is the rate of change of angular displacement with respect to time. And if you remember earlier, we had angular displacement as this angle here. So angular velocity is how quickly does this angle change. It's the rate of change of angular displacement. Theta is the angular displacement, t is the time taken, and the units of angular velocity is rads per second or radians per second. Looks like that. If you consider this red point and the blue point on the wheel again, the rate at which the angular displacement changes for the red dot and the blue dot is exactly the same. So even though v red has a smaller linear velocity than v blue, it has exactly the same angular velocity. We can link linear speed and angular velocity, and we can do that using this relationship, v equals omega r. Let's remind ourselves of the equations. Linear speed is equal to v equals 2 pi r over t, the units are meters per second. Angular velocity is omega equals theta over t, and the units are radians per second. And we can link linear speed and angular velocity using this relationship. Do you remember when we were discussing the satellite going round in a circle and we analysed the velocity vectors to find the change in velocity? And what we found was that the acceleration was always directed towards the centre of the circle. We found that out earlier, but we didn't have a formula to tell you exactly what magnitude of that acceleration was. Now we have a formula. The centripetal acceleration is a equals v squared over r, and it has meters per second squared units, just like in linear motion. But we also know that v equals omega r. And if we substitute that into here, we end up with a range of different expressions for centripetal acceleration. Similarly, Newton's second law states that the resultant force equals mass times acceleration in the direction of the force. So if we have acceleration towards the centre, we have force towards the centre. And the force is equal to A. That means we can add F equals ma to our acceleration equations and we end up with these equations for centripetal force. The force is always measured in newtons. If an object is in circular motion, there's a force towards the centre of the circular motion, then that force has to have a name. We talked about forces earlier. We talked about all sorts of different forces. This force has to have a name. It can't just be a centripetal force. It has to have a force that's causing this centripetal force. And one of the skills of IB physics is identifying the type of force. Now, if we're looking at a satellite going around Earth, the type of force that's causing that centripetal motion is a gravitational force. If we're looking at a ball being swung around somebody's head on a string, then this force here is tension. Head to your revision notes, and in your revision note template, include equations involving centripetal force, acceleration, period, frequency, basically all the formulae we've just written down, get them in your notes, and then do questions 1 to 7 in A2 Part 3 of the knowledge questions. Let's start applying all our knowledge into exam style questions. Let's move on. Let's go.